All right, we should be good to go.
Thanks. Hello, everyone. Good morning, good evening, I guess, depending on which time zone you are in. I guess we have folks all over the world. So my name is Seema Sundara, and I'll be chair for this tutorial session. So I want to welcome you all to the tutorial Visualization Systems for Linked Datasets. Maria Cremeda and Verena Cantere are the authors for this tutorial. Verena Cantere is an assistant professor at the School of Electrical and Computer Engineering in the National Technical University of Athens. Maria is a PhD candidate under the supervision of Professor Cantere, and she's working on big data exploration and visualization techniques. Both of them are part of the Knowledge and Database Systems Lab in the university, and Maria will be hosting the tutorial today. So before I hand over the session to Maria, just a couple of bookkeeping reminders. By default, all the attendees are muted. So if you have any questions, please either post them in the Q&A box that you see at the bottom of your screen or in the Slack channel that is dedicated for this tutorial. And I will pass them on to Maria as needed, either during the session or at the very end. So thank you, and Maria, it's all yours.
Thank you, Seema. Thank you, everyone, for joining this tutorial. I will admit that it feels a little bit awkward to talk to my screen and not see each other, but hopefully it's all for good. And you will be able to enjoy my presentation and follow me in this exploration of visualization systems for linked datasets. Before we begin, a few things about me. Seema already introduced me, so there are not a lot left for me to say, but that I have my degree from the Electrical and Computer Engineering from the National Technical University of Athens, and I'm currently a PhD candidate under the supervision of Professor Verena Cantere. If I was to give a summary of my interest, I would say that there are three things that define me: databases, big data, and coffee. So unfortunately, we won't be able to have altogether a coffee break, but I will be able to talk to you about the two other things that I'm very passionate about: databases and big data. So before we go into details about visualization systems and all that's there about techniques and processing and all that we are going to see next, I would like to start a little bit with the title of the presentation and focus a little bit on the linked datasets. Most of you have probably already heard the term, or you have a short idea of what a linked dataset is, but I would like to discuss with you a timeline just to see a little bit closer how what we now call linked dataset begin. So if I was personally asked to pinpoint the first time that we have what we call linked dataset, I would go a while back. I will go in the 1999 when Tim Berners-Lee actually made the first client-server architecture and created the first web client. I don't know how many of you know the story behind of this first web client, but the problem that was everyone facing was the phone book for the CERN Research Institute. And the question was how they could have this information centralized and accessible to everyone. And the idea was to try to centralize it and all that, and more or less created what we know now as World Wide Web. That was only the beginning. Very soon, the need to add semantic information and to make the data interchangeable, shareable, and useful to all came up, because the information was there, but most people didn't know about it or could not access it. And then two efforts materialized on that part. And they, I would say, started at the same time, developed almost in parallel, and tried to tackle the same challenge, but with two very different approaches. So in 1999, we have the semantic web, an effort to provide understanding and meaning to the content of the datasets, and the RDF framework, an effort to provide structure and give the information a specific format that would support the interchangeable. These two efforts, I would say that are complementary, and they tackle the same challenge very differently, but in two very useful ways. And I think that was proven later on when in 2008 we have the SPARQL, which is the semantic query language for databases, which is actually the first effort that we have about querying and accessing systematically all the data sets that are available as RDF. After that, I have in my timeline the big data. The truth is that if someone is asked to pinpoint historically, if you wish, the beginning of the big data, it's not an easy task to do. We can find mentions of the term big data as early, I would say, as 1997, when it was first found in the ACM Digital Library. There, the big data started to format in a sense of data sets that were too big for the main memory, and even maybe too big for the local disk of a personal computer. Nowadays, when we refer to big data sets, we refer to terabytes or petabytes of data that are produced in buckles and from social media maybe, or other sources that produce quite a volume significantly larger than gigabytes as it was initially referred to. I would say that intuitively, big data, the initial definition was to describe them as what does not fit in the memory. So depending on the era or the time that we are discussing, pretty much big data is what we cannot fit in the memory of a personal computer or let's just say easily accessible device. For me, if we want to go a little bit deeper in the big data and how we are defining it and describe them, I would prefer to stick with the list of V's. So the list of V's started early on with the big data. Initially there were 3, then they became 5, then they became 7, and nowadays we have a list of 10 V's. I'm not going to present you here the complete list of the 10 V's, but I'm going to focus on the previous version, where the list only had 5 V's. I do this mainly for 2 reasons. The first one is because 10 V's would be too much to follow throughout the presentation. And the second one is that, at least in my view, the V's that were added after these 5 have a lot of overlaps, many specializations, and there are many domain-specific ones that do not actually add to the essence of the definition. There are more to support different categories or subcategories of the data. So the first V, I think it's obvious that it would be the volume. We discussed it already, that the volume of data that qualifies them as big is very dependent on the time that we're discussing, and of course the topic area. Indicatively, I would like to say that every minute we have approximately 500,000 photos in social media and 500,000 posts only in Twitter. So this is quite some volume of information that is produced today. Now, the second V for the big data is the velocity. The velocity can be interpreted in 2 ways, depending on the perspective of who is actually interpreting the term. On the one hand, velocity may refer to how quickly the information flows. This means that we have an information that is being created and it's constantly being updated, and we have a flow, a data flow that is processing and analyzing this information in order to provide some result. For example, for financial sector, that's very easily grasped, because there we have the transactions that affect the prediction of a stock market, for example, or how well or bad it goes within the day. So in these cases, when we are referring to velocity, we are referring to how fast from the production of the information we can reach the end result, which is the data analysis. On the other hand, velocity may refer to the tempo that the data are produced. I will just give an indicative example. For every single second that passes, in YouTube, we have about 10 hours of video uploaded. This means that the velocity of videos uploaded in YouTube is very high and very intense. So depending on the perspective, this is how velocity can be interpreted. Next V is the variety. When we are referring to variety, we are referring mainly to the source of the information. So there are many sources available that produce big data. We have already discussed about financial. We can discuss about the Internet of Things, sensors that may be available. We can say again the social media, of course, that play a huge role to all that, but all the other material that is available. And the important thing about the sources is that they have a credibility that follows them, and they imply the trustworthiness of the data themselves. So it is very different if we have data that are coming from users, from crowdsourcing, or from official organizations. It's completely different if we are talking about data published officially from an organization or data collected through any other process. Now, the next V, the fourth one, is veracity. Veracity, we can say it's used in the place of quality, just so to keep the V's in the list. It's more or less there to remind us that we always need to question this data, because occasionally the source is not very reliable or it's not well known, and that there are many things that are not very clear. For example, it's not mandatory that we will have a complete data set, or a data set that it is clean, or a data set that it is accurate. So if we discuss, let's just say, a network of sensors, no one can guarantee that the sensors measuring are accurate, or the information that we are having is of accuracy. So veracity is there to depict the question mark about how the quality of the data is interpreted. And the last V that it completes the list of 5, which was added only recently, is the value. So I would say that most of us here, and anyone who has done some research in any field, usually associates data with knowledge or with a source of knowledge, because you usually need some data to start some analysis, some exploration, and reach some conclusions. I believe that this is the main reason also that it took quite some time to realize that the fact that we could have reliable sources and quality of data didn't necessarily mean that they had to offer something additional, or that there was knowledge that could be extracted from them. So I would say that time-wise, with the boom of the Internet of Things, when the smart homes and the cloud storage for many sensors started to become very popular, it sort of became apparent to everyone that the value is not something to be taken for granted. So if, for example, I have the temperature from every house in a block of houses, this probably doesn't give me anything of value to further proceed with it. So probably it's not a very useful data set all in all. So why I chose to discuss with you the exploration of big data through visualization. If we reverse the question and ask ourselves how we can explore the big data, we will have to start by admitting that there are thousands of datasets available, that they cover a wide range of domains, that these datasets could be of interest to many, especially users that are not very familiar with what we call semantic web or SPARQL language or the RDF model. They know that the dataset probably has the answer to a question that they need to answer, but they don't know how to discover this information or access this knowledge. And I have added here the picture provided by the linked Open Data Cloud, which showcases only available datasets. I would say for sure that even experienced users that know how to look for these datasets or how to access them we would have trouble to pinpoint exactly the dataset needed for the specific work that they want to do. So all in all, we have an issue of how we are going to make accessible this information to a wider audience. So why visualization? If I was to sum up only in one phrase, I would say that a picture is worth 1,000 words, as the picture from Load shows us here. Now, okay, we said that we know that we want to explore big data, and we said that we know that we want to explore them through visualization. But that's not the end of it. That's actually the very, very beginning of it. And I would say that there are many challenges associated with such tasks, all of them coming from the V's that we already discussed. And I want to say that each V can be associated with a group of challenges. I have summarized them here in order to provide you an idea. So let's just say that let's just say volume. Okay, the volume in itself implies that we will have too much information. This means that our exploration should be interactive, that we cannot just provide the user a static image and expect him to understand what it's shown there. We discussed velocity, which means that datasets grow too fast, so we need systems that are scalable and can handle the volume as it increases. And we discussed variety. We said that datasets are expected to have quite a few different characteristics. So our system should be characteristic agnostic and be able to adjust to the characteristic of the dataset. And we also discussed veracity. So we said that we expect the datasets to have mistakes, to be incomplete or inaccurate, which means that the systems should maybe provide some type of validity, but for sure be resilient to any problems or issues regarding the data that they are receiving or they are trying to explore. And in case you are keeping count, I left one V out of this slide because I wanted to emphasize it a little bit more. And I wanted to discuss a little bit in length about the value. We said that this is something that was added recently. And it was added recently because we realized that it's pointless to have data if we cannot exploit them. And it can be said that there are many ways to exploit a dataset. So given any dataset, different users will have different needs, different use cases, different applications, will request different functionalities, making it even more difficult to have a generic approach or a generic system that we cover all. I have identified some key points that for sure all systems should provide. Having already seen the challenges and the nature of the big data, we would say that we will expect the navigation of information to be interactive, responsive to the user needs, to have a presentation that will be flexible. So if I'm a very novice user, I would probably need to see something very different from someone with more experience. We will actually like to see multiple levels of details. We already discussed volume of information and different sources. So this means that not everyone is interested in everything. And of course, accessibility, because big data sets require quite some heavy, not only storage, but processing infrastructure, which we should not expect the users to have. Now, I will move on to the visualization techniques that have been exploited so far. I have divided them in 6 categories. We will discuss a little bit about semantic browsers, hierarchical visualization systems, graph visualization systems. Then we will move on to tools that are visualizing SPARQL endpoints. And the last 2 categories may not seem directly, let's just say, connected with the visualization topic, the query writers and the Schema Identifiers, but we will see through examples of tools that many tools tackle the problem of query writing and Schema identification through visualizations, aiming to support inexperienced users in better exploiting the available information. So we will begin with the semantic browsers. I think it comes to no surprise to anyone that when the World Wide Web turned into semantic web, the first instinct of everyone was to turn the web browser into a semantic browser. What a semantic browser does is links different data from different sources, following the interconnections between them. It follows very closely the semantic web standard, and that's what I would say defines them, because based on the web semantic standard, they can have a very specific baseline and that does not change. So they know that if a dataset is provided according to the standard, then this browser can support it. Now, let's just compare the pros and the cons. On the positive side, semantic browsers can more or less link any data source. They are designed as our regular web browsers, so whatever is available online can be linked in a semantic browser. It is very easy to provide interactive exploration based on their nature. Most actions over a browser is very intuitive, because everyone is very experienced with the web browser. So jumping from the web browser to the semantic one is very easy. And I would say that the key positive thing about the semantic browser it is that it highlights the semantic content. As weird as it sounds, the fact that it does not focus only on the linking of the data, but it also focuses on the semantic information is very, very, let's just say, good for the intuitive analysis of the data. Now, on the negative side, we already said that the semantic browsers are more or less like a web browser. This means that as we start with a web browser from a specific page or source, this is exactly the same thing we should do with a semantic browser. We should start with a specific source or a specific keyword. Obviously, only sources that are compliant with the semantic web can be included in the browsers. And what else comes into play here due to the focus on the semantics is the amputation. So terms that are very similar or have close related meanings may be difficult to locate or differentiate. The first tool that we will see as a semantic browser is Tabulator. It is specifically chosen because it is a tool developed by Tim Berners-Lee as the first tool that we will see. It is a generic browser. It started as an experiment trying to see if there was possible to have a generic solution that can be meaningfully applied to the RDF dataset. So it avoided domain-specific visualizations and tried to recognize and follow links between RDF resources based on the user explorations. I will indicatively say that the first effort was started by a very simple, if you wish, but also very common use case. So the idea behind the tabulator was that, let's just say that you receive your transactions from the bank, and you see in there that there is one that you don't remember how it happened or when it happened. You check the date and you go to your calendar, but you don't find any appointments or anything else that can trigger your memory. And then you check your images or the photographs that you have taken that day, and you realize, oh yeah, I was at the carnival, for example, and that's where this transaction came from. So as you can see in the screenshots that I have provided, it tries to combine maps, tables, calendars, and time series in an effort to intuitively answer questions that need more than one source. A next approach that we will discuss is the linked data visualization model. You see here a little bit of the architecture. The idea behind this model is that the semantic data can be visualized using information visualization techniques that are already available and established. So it provides dynamic data extraction and visualization. It presents data as stream maps or maps as it is applicable, and it is focused on the overview, something that we will see. It's very common throughout the tools that we will discuss, and provides details only on demand. It actually, as you can see in the architecture, tries to establish a modular data flow. This means that it allows the user to choose intermediate blocks, and maybe some of these visualization operators or analytical operators can be changed. That implies, though, that the user is familiar with the data set or its contents or the value that he wants to extract from it, which is not always the case, of course. And even though the overviews produced by these can be very good to the overall understanding of the information, as we will see again in the following tools, sometimes overviews obstruct the user from the details and may lose part of the information that can be key to the understanding of the data set. Next, we will see the RelFinder. It is actually a tool that aims to find semantic relationships between selected elements. Here, the disambiguation is done manually because the tool needs to establish that the nodes selected are unique. And then it tries to establish all the relationships between them. It can be specified the path or the relationships that will be used in order to link to nodes. I would say that, as its names imply, it is the ideal tool for relationship finding. So if someone has two entities and needs to see if they are connected in any way, RelFinder does that in a very straightforward way. After, though, finding the connection between two entities, especially if there are too many or too long, it might be very difficult to analyze and extract additional information. So that's something that it's not the main goal of the tool, so it's not that well taken care of. Next, we have Explorator. Explorator is a search tool for the RDF graphs. It is providing its own interface metaphor, meaning that it's trying to present the information not as a table, tree, or graph that we would expect linked datasets to be presented as, but as an let's just say custom interface metaphor, which is very close to the RDF model. So it showcases resources, the trickles of the information, and sets of information. As you can see in the screenshot that I have here, it more or less tries to describe the tree, or if you wish, the paths that create the resources. And it also provides a query by example interface for the querying of the data, which can be helpful to people that are very familiar with that. Now, the next next we have the hierarchical visualization systems. So hierarchical data are data that can be arrayed in the form of tree. It means that the nodes are fully connected, but it means also that we don't have any cycles in the data. Usually hierarchical visualizations can have two types. It's the node edge graph layout, what you would expect us to see a tree like output from the visualization, and the space filling approaches, which focus mainly on creating nodes of relevant sizes that the size is indicative of their role in a hierarchy. We will focus mainly on systems that present the data in the node edge layout. And it is also worth mentioning that hierarchical systems are usually very focused in aggregation, filtering, or the creation of some supernodes that are used in order to support the hierarchical model, because data sets on their own are not expected to be hierarchical. So the pros and the cons of that, I would say that hierarchical visualization are based and are exploiting the fact that the semantic ontologies have a lot of hierarchies. So it is very easy to establish the hierarchies of the data based on the semantic annotations. We can also say that exploring data in a tree-like format can be a little bit of intuitive, meaning that it moves from general to specific or from specific to general. That can be easily understood by a user. Tree-like structures are very well known and they're available a lot. So this is also something that we should keep in mind when we are discussing hierarchical visualizations. And another thing that these systems have as a positive is that they can produce a very good and very well structured high-level overview due to the hierarchical visualization. Now, on the negative side, we can say that they can be applied only on specific data sets. Finding acrylic data sets is not very common. So most of the approaches that we will see either force data to become acrylic, or they are focusing exclusive on data sets that can comply with that. Sometimes they result in loss of information because they try to create the hierarchy and the supernodes. And they also allow the navigation of the information based on the hierarchy that they have created, which means that the information is inaccessible from the same level. Sometimes this is not very intuitive, especially if someone is looking for something very specific in a data set, as it may mean that he could be very close to the information that he seeks, but not very easily to reach it. If we move to specific tools that cover this visualization, we can start with GraphView. It's a system that, as you can see in this diagram, tries to provide, to use the graph topology to create clusters. Its main aim is not to require extra information, either semantic or from the user, and to try to provide interactive navigation of large graphs. It is based on a client-server system, because it needs to take advantage of a permanent storage to handle bigger data sets. Its main issue is that because of the way the clusters are formed based on graph topology and not semantics, it's sometimes difficult to give a meaningful label or a meaningful summarization or the specific keywords that are needed in order to make the clusters understandable by the users. And so sometimes there is a cluster, but it's not very well specified regarding its content. And that could be very disengaging to the user. Next, we have Tulip. So it is once more a tool designed over the principle that the overview is key, and then filtering or details on demand can be provided to the user. It tries to introduce a data type that will support the visualization of the graph hierarchy and creates clusters, here giving emphasis not on the graph topology, but on the semantics, and make sure that each cluster has somehow a semantic connection. So the semantic information is transferred to each cluster, to its supernode. And it can process quite large graphs. And we have here 2 screenshots I have used. It's the balloon and the country droning. And in case you are wondering, because they look spectacular, but they are not very intuitive, they are presenting 110,000 files from a file system, aiming to detect any duplications, hidden files, or problems with the directories. So as you can see, the end result is very appealing regarding a graph, but may not be very intuitive regarding the exploration of the information. Next, we have the GMine tool. It is a tool that is once again based the clustering on the topology of the graph. So here the METIS partitioning algorithm is used. The METIS algorithm is an implementation of the K-way partitioning algorithm. And it more or less needs to know the number of the clusters that should be created in order to try to do some optimization regarding the connectivity in each cluster. Now, each partition is visualized once more as a supernode, and details of which supernode are only available on demand. And as it is expected, the quality of the end result is very closely associated with the dataset, the nature of the dataset, because for cases that partitions are not very easy to create, or that the semantic information is not well depicted in the graph topology, the communities may include information that it's not coherent semantically, and thus making the exploration very difficult and very challenging. Here, the screenshot here shows a label search for an author in the DPpedia dataset. The initial results is about 500 nodes, and because then it was established that there is a limit in the path between the entities, the end result shown in the latest panel has quite few, like 50 or so nodes. As you can see, the more the information is filtered, the easier it is to interpret and understand and to locate things of interest. The next tool we are going to discuss is GraphView. GraphView is actually the only hierarchical tool that allows the user to explore the dataset through different views, but also to edit the hierarchy and the views that the user is using. It starts initially by taking into consideration the graph topology and creating some hierarchies for the user to see, but then the user can edit these hierarchies and eliminate any errors or anything that it not suit its exploration needs. It is a tool that, let's just say, bases a lot of its output in the user ability to understand the dataset and understand how the dataset should be processed. But it's also a tool that can visualize on the same time many different views. So here, the screenshot that we see actually visualize two different things. It visualizes at the same time papers that have a specific keyword in their title, the keyword interface, which are the pink ones. And it also visualizes papers where McKilland is an author, which is the green one. So as you can see, it plays around a little bit with how we would draw sets of information, making a little bit of intuitive to understand if sets have overlaps or if they are disengaged. Moving on, we are going to discuss the graph visualization systems. Graph visualization systems do things a little bit differently. There are the systems that do not try to create their own data model or to change the way the data are to be shown. They stick with the intuitive presentation of the subject, predicate, and object, which is the structure of the RDF model. And they provide access to the information in one level. We don't have the exploitation restrictions that we had with the hierarchical systems. And to go a little bit into more detail, the graph visualization systems allow us to explore all the data objects in the same level of exploration. The graph structure used, we can say that it's very intuitive because it's very close to the RDF model and the way the information is structured there. And we can say that the graph visualization systems have very few limitations regarding the input of the data set, mostly because of them closely following the RDF model. On the other hand, trying to visualize triplets of information in one graph makes datasets with billions of elements quite daunting. We can say that the volume is very crucial. So most of the systems that we are going to discuss now have introduced some type of pre-processing to support that. It is obvious that not all the information would fit in one screen. Here we don't have the hierarchical summary that can help us out with fitting even the high-level information in one screen of the user. And as a result, there is a need to hide some of the information, which may result in loss of value for the dataset and exploration. Now some more specific examples. We have LODWheel. We'll start with that. As you can see here, we have a very impressive chart visualization, which showcases the DPpedia entity of the Italian company Fiat. You can see that the information is presented as a graph. So what LODWheel provides is that it did an exhaustive research on available JavaScript libraries for graph visualization and RDF visualization, and decided to combine the two higher ranking ones, aiming to offer a global solution that would be cross-platform and available for all browsers. As you can see from the architecture that was designed, it tries to disengage the process of actually accessing the backend with the data set. So it can offer a plug and play solution. The only drawback of this tool is that, for example, for the DPpedia case study, the information was grouped beforehand in 14 categories, and the visualization was specified for each of these categories of data available in DPpedia, meaning that if someone wants to change the data set, it would need to provide a different categorization for the data and specify the visualization that will be needed for them. Lodlive is another tool that builds upon SPARQL endpoints and allows the user to browse leak data, mainly by navigating interactively over the graph. So as you can see in the screenshot, each node is presented along with its neighbors, and the user can choose how to navigate it. Again, starting by given URI. What LODWheel adds here is that it creates spatial maps and collections of images as they can be extracted by the endpoint. So if the user chooses to do so, the spatial information can be seen in the map as we see here, and the images can be shown in a gallery. That can provide additional intuitive exploration, I would say, of the data sets. Next, we see here the ZoomRDF. ZoomRDF focuses on something that none of the tools we have seen so far are focusing. ZoomRDF tries to optimize the space of the screen that the user has in front of him. So it creates a space optimized visualization algorithm. And then it tries to display as many sources as possible in the display. On the same time, in order to avoid overwhelming the user, it creates a fisheye zooming concept, which means that based on the user actions and user choices and selections, some nodes are shown as larger or smaller, focusing the information of what it is interpreted as of interest to the user. This means that the user has access to quite more information that it would otherwise have, but also that the focus is not lost in what it is important for him to explore. Next, we have here FlexViz. FlexViz offers again a node-edge visualization. It offers, however, an additional level of filtering, but it's based mostly on search and navigation criteria. Its main aim is to reduce the amount of data that are exposed to the user or that they should be handled by the tool, and tries to provide the subsets that are meaningful, semantically meaningful to the user. And it also employs details on demand. So based on the user exploration, it could provide more information as needed. In the panel here, we have the visualization of the mouse adult anatomy by biological data set, and shows the tree hierarchy on the browser, and also the rendering of the graph. And as you can see, all the edges are have a direction in order by how the entities are connected. And also, as you can see on the panel, it is very easy to add or remove filters. Last but not least, I would like to present you the interactive visualization of large graphs. This is a tool that I have developed as part of my PhD. The idea behind it is to avoid any type of information withholding from the user, and try to find a solution that will allow us to show the complete information to the user. So for each input data set, it is processed and it's mapped to one continuous graph in the two-dimensional space. It is stored in a graph database, and then it is available through a client-server architecture for the users. And on top of that, based on the properties that are stored in the graph database, the users can have additional filtering and abstraction functions that allows them to further support their exploration and their navigation. As you can see here from the data flow, the tool can work in any size of screen, and the volume of information that is available to the user is accordingly sized down or up based on the screen size. Because the graph is one and continuous and stored in a graph database, this allows the user not only to explore the information, but also to intuitively understand where this information is located, because if he moves along a path, then he can traverse the same path backwards and find himself again with the same information. And that concludes the discussion about the graph visualization systems. The next technique that we are going to discuss, it's about the SPARQL endpoint visualization tools. So SPARQL endpoint visualization tools, the idea, I think, behind them started by the nature of the SPARQL endpoints. If we keep in mind that SPARQL was designed in order to provide the way to access semantically the RDF datasets, the SPARQL endpoints are mostly designed to support machine-to-machine exchange of data. This means that they offer the information in raw RDF format without any interpretation, without any visualization, without any support for human exploration, and without any type of filtering or validation. So what the SPARQL endpoints offer is a gateway to many resources and datasets that are, though hidden behind a very machine-friendly format. That's why SPARQL endpoint visualization tools were created. These tools can very easily adapt to any endpoint because they are based on SPARQL queries and what the SPARQL language has to offer. It is very easy to adapt any endpoint to them. And they have mostly been designed based on the expected responses to SPARQL queries, meaning that they have a very complicated but specific input source, which is the results of the queries. On the contrary, now the usage of these tools may be counterintuitive. So far, solutions we have seen are very agnostic regarding technologies of semantic web or SPARQL. But most of the tools that we are going to see now will require the user to at least have some understanding of the SPARQL language. Most of these tools are very restricted by the limitation of the endpoints themselves. It is expected that the people providing the resources will have some limitations on the number of queries, the size of the responses, and also there are cases where the endpoints are not available while the tools try to access them. So if we go into more details, we will discuss first the Visualbox. It is the first effort for non-programmers to access linked data and to provide some web visualizations of them. So it, as you can see on the screenshot, it more or less provides a complete data flow, which means that it allows the user to choose a SPARQL endpoint, write down a SPARQL query, this is processed, the result is retrieved, and then the result is visualized if it's applicable, as we can see here, for example, in a map. What Visualbox does in order to protect itself from the potential lack of in SPARQL endpoints is that it creates a cache mechanism that allows some of the data or some of the previous executed queries to be available even if the endpoint itself is not. Next, we are going to see the linked data query wizard. This is also a web-based tool. It provides access, filtering, and exploration capabilities over linked data sets that are stored in the SPARQL endpoints. What it tries to offer, in addition to any other tool that we have seen so far, is that it tries to turn the structure of the linked data into tables. So based on the concept that users are more familiar with the relational model, and that the graph structure is not as intuitive as the tables that they already know, the tool tries to provide the outputs and information in tables. And it also tries to use elements from current search engines that are familiar to the users. As you can see here, you can see that the result of a query has been visualized in a table. We can say that this is an approach that can be very useful to inexperienced users, but it can only be applied to queries and datasets that can actually support such type of visualization, that the semantics of the information allows it. The last tool that we will see here for the SPARQL endpoint visualization is the SPARQL-vision. Again, it is a tool that has been developed in the course of my PhD research. SPARQL-vision is a web-based tool. its main focus is to try and offer the right visualization tool for the right query, meaning that when a user forms a SPARQL query, this is analyzed based on a decision support system and some very specific rule-based decisions, as you can see in the tree. And based on what it is the information in this query and what the data retrieved are, then the information is visualized. The visualization can be a graph, or it can be a chart, for example, an area chart or a pie chart, or even a map chart if we have spatial information. And in addition, the tool allows some interactive filtering in order to facilitate the user to better understand the information that has been retrieved. Next, we will discuss query writers. As we already said, the SPARQL language in itself is quite complicated because it tries to follow the RDF model, which is machine-oriented. It is very, whoever has tried before would know from personal experience that the SPARQL language is not very intuitive, and it's very difficult if you're not very experienced or if you don't try a lot to create meaningful queries or queries that will provide you with the answer that you are looking for. SPARQL does not behave in any way or sense like the relational models that most of the users are familiar with, making it even more difficult. So the idea was that it would be very useful to support novice users in understanding the SPARQL language and offer support to the creation of the queries in a way that will make sense and would be very meaningful. On the negative, let's say, side of these approaches, most of these tools have some limitations to the querying capabilities that they allowed. And sometimes they actually do hide the actual SPARQL code from the user, feeling that a more graphical view would be easier to interpret and understand. We will see as a first example the SPARQL Builder. This tool is addressing users that have no knowledge of the SPARQL language, and the queries can be generated in a more, let's just say, a graphical way, as you can see from the screenshot that it's here. The SPARQL Builder is also incorporating Togo tables, which is a web application that allows biological researchers to upload their data and also to create their own annotations. This means that it can very easily facilitate the users in exploring these datasets that are available there. As you can see in the example here, we have some type of proteins that are visualized. And if you select one of the paths, then the corresponding SPARQL query is created and queried over the dataset selected. Which is very intuitive but it's very domain specific. MashQL is another approach that offers query by diagram. It actually creates its own language for this querying, and the people are more or less asked to build their queries by connecting nodes. Each node represents an intermediate search result or an endpoint. And it more or less allows the querying of a source without any understanding of the schema of the information, of the structure of the source, of the SQL language, or anything at all. The screenshot here shows a person that tries to look for a job. So it starts with two sources. in order to try and query the Google base and the jobs UK. And it tries to merge these two results into finding the right, let's just say, openings for jobs in order to apply. So as you can see in this query, even though it combines two sources and quite some filtering, no specific query language has been used. So no SPARQL or anything strict like that. The next tool is SPARQL Filter Flow. It's an approach to actually create, to rather than write SPARQL queries, to visually create them with flow graphs and filters. And as you can see here, there is a graph which corresponds to the SPARQL query presented in the bounding box. And the query can be created here to exclusively using graphical elements. Last but not least, we have SMART. SMART stands for Semantic Web Information Management with automating the reasoning tool. SMART tries to do something quite innovative in the sense that it actually asks the user to type in the query using a language, a common used language, and this is interpreted in a graph structure, as you can see, which is then interpreted in a SPARQL query. Again, here the effort is to focus in experienced users that want to query data that but they don't have the knowledge to go into details regarding architecture or schema or RDF. And the last category of tools that we are going to discuss are the schema identifiers. For these tools, the idea behind the schema identifiers is that there are already a lot of available solutions for relational models, and that there are a lot of users that are very familiar with the relational model. So if we could identify the schema of an RDF dataset and provide that to the user, then it will facilitate the exploration and the understanding of the resource. So on the positive side, the schema identifiers are very good for users that are knowledgeable over the relational models and can support a lot the use of already available solutions, and they can support the understanding of the information from a wider audience. On the other hand, schema identifiers are very demanding on the endpoint itself, meaning that they require a lot of queries to be addressed by the endpoint and answered back in order to collect the information. And they may face two very important challenges. The first one is that it is not a given that the dataset explored would have a schema for the data that would be extractable. And it is not also certain that the extracted schema is actually the right one for this dataset. Having said that, it is very easy when you discuss RDF, which is which can have many different sources and very different representation of the same meanings, to extract a schema that will conceal some information that could potentially be of interest to the user. Now, a tool here that it's of interest is ViziQuer. Again, here it asks the user to provide the address of a SPARQL endpoint. What the tool does, it starts with a series of SPARQL queries, and as the responses are received, then these are visualized as a schema. The queries are predefined so based on what it is exactly by one, the schema is designed. The tool itself is quite time consuming and demanding regarding the processing. And it is very dependent on the ontology size of the dataset that it's explored, and the speed, of course, of the SPARQL endpoint, and any type of limitations regarding data sites, any limitations on the size of the responses from the endpoint, which may conceal again information. And another tool that it's also of great interest here is the Tbox-based visualization. Tbox is usually a term used to define the schema, to call the schema of a SPARQL endpoint. So this visualization tool aims to extract this information of the schema that the data are using. Again, the tool is based on a series of SPARQL queries that are used to extract this information. And the information is incrementally added as an interactive graph visualization. The information here is not presented as we saw previously in a schema-like way, but more of a graph-like node link-based visualization. In order to provide to the user an understanding of the hierarchy of the structure of the data set and give him an overview of the information that it is available there. So these were the tools, these were the visualization techniques and the tools that we had to discuss today. I would like to summarize with a few important messages, to at least to my opinion. So if the question is if we have a solution for any given problem, then the answer is that no, not all problems have been addressed, but for most of the problems that are out there, we can find the right solution. And in order to do that, there are some very specific things that we should take into consideration. The first is the target audience. If we are addressing users which have no experience of the semantic web, some experience of the semantic web, or maybe they are more familiar with query languages and SPARQL endpoints. The second point that should be taken into consideration is the purpose of exploration. As we saw before, some solutions are targeted in providing overviews, some others are targeting provided specific details and access to the complete information, while others are targeting the overall data format and the schema of the endpoint, and could provide very different information about an endpoint and have different uses of that. The other point that should be taken into consideration is the dataset of interest. So what is the dataset I'm interested in? If I'm interested in combining more than one data, or if I'm interested only in one source, and what's the characteristic of this source? And last but not least is how I want to access this information. As we saw, most of the tools discussed are hardware-based, but there are also some desktop solutions or some solutions that are provided in order to process the dataset locally. So based on my needs and how I want to explore these datasets, the right one should be chosen. And of course, it's not only to find the right solution for the problem, but it's also to find the right solution for the given data. What we stress out throughout this tutorial is that not all datasets can be explored through all the discussed tools. We saw that some tools had specific limitations. We're asking for example, the SPARQL endpoint or an acrylic dataset or semantic annotations or compliance with specific models. This means that given the dataset that we want to explore, some only solutions are applicable, while others are not. The specific characteristics of the dataset is what will define which solutions can be used and which cannot be used. And of course, it's very important to understand which of the solutions available can support the data set that we want to process. And we will discuss again the 5 V's that we discussed initially. And we said that they are there and they are forming the challenges. So if we are to discuss where are we currently and what are the limitations that we have and what needs still to be exploited, I would say that the volume of the big data is something that has been tackled. Most of the solutions that we show provided solutions that could handle quite large data sets or pre-process quite large data sets and provide access to the information afterwards. I would also say that veracity has been tackled in the sense that no system is strictly expecting a valid data set or a very accurate data set. And I would say that variety is something that is very difficult to tackle. We already said that not all data sets are applicable to all the solutions, but also it is something that maybe not of the key importance because mostly we won't want to combine data sets that are completely different. I would like to stress out though velocity. I think that it is the main open research issue because most of the solutions that we show require some type of pre-processing in order to allow the users to have access to the information. And that means that it takes some time from when the information becomes available to when the user can have access to that. And last but not least, we have the value. We can say that the value is and will be an ongoing problem, or if you wish, a research field. There are many users, there are many use cases, and there are many ways that the same data set or the same information can be exploited, meaning that value can be seen from very different domains and have very different characteristics. That being said, it means that data sets, as long as we have more data sets available, there would be more need for exploration and different ways that we can extract that value. Thus, I feel that it is still an ongoing research subject. Thank you all for your attention. If you have any questions or anything that you would like to discuss.
Thanks a lot, Maria. So I'll just open the floor for questions. So if folks have any questions for her, please feel free to type it in the Q&A section.
And also just to add on the last slide of my presentation that I will not show you now are all the references used for the creation of this presentation and all the papers that are addressed or used. So if you have any more questions or you would like to see additional.
So Maria, there is one question from Ahmed Aldavi. And are there any specific techniques that are directed to map visualization or geospatial visualization?
I would say no. Usually the tools that are targeting RDF datasets are not focusing so much on specifically spatial information because the percentage of the information that is expected to be spatial in such data set is small, like it won't be a complete spatial data set. So in that sense, I would say that most of the techniques try to be hybrid and not focus on spatial information, though there are examples and there are tools that try to put on maps parts of the data set that are spatial, that offer this information.
Thanks. So maybe while other folks are thinking, I just have a question, right? So I was looking at what about inferred triples, right? So when you talk about RDF, right, there are asserted and inferred. But I think in the tools, I just saw in probably one of the tools, I think the Smart, which said it also compiles the inferences like ahead of time. What about the other tools? Or do they have any way of showing inferred triples separately from the asserted ones?
Sorry, I was muted. You mean like storing locally some of the information, if I understand the question?
No. So when we have the RDF triples, right, there are these set of asserted triples, which is the source of truth, right? But on those we can run inference and add a lot more value to the data. So do any of these visualization tools, when they display the results, do they distinguish between asserted and inferred triples, or do they treat them as same?
No, they treat them mostly, I would say, the same. Okay. Yeah.
So maybe I'll ask one more question. Right? So that is, I think you had mentioned that the veracity problem, right, in data is already being tackled. So maybe could you shed some light on that? Because to me, especially when we go with like data out on the social network and stuff, right? The veracity or the truth behind data or data cleansing still remains to be a big challenge. So
I would say there are two ways this, let's just say, quality issue has been handled so far. The one way that it is handled is like with sort of an indifference. So this is a data set that I have, and I am processing it and exploring it, and I am providing it to the user, naming my source and saying that the data are provided as is. And then there are so this is mainly addressed to inexperienced users that just want to know what's there and want to have access to the information. And then we have like the more professional, if you wish, approach which is coming mainly from data analysts, that they need to extract value that goes beyond the exploration of the data set itself. So they want to process this information and create something different. The truth is that there is a research field on its own. Many times there are examples out there with systems that fail and fail dramatically and failed after the investment of a lot of effort and money, just because they trusted some type of input data sets that were coming either crowdsourced or from sources that were not validating their information. Yeah, and created a lot of issues. I would say that the notion that if the source is trustworthy, then the data are trustworthy too is no longer valid. We have seen examples that data set provided by well-known organizations are not of high quality, or they're not devoid of noise. And I would say that most of the research there is focusing on trying to find the valid data through that. So limiting the volume, because the volume is what we have, and trying to do smaller data sets, but with higher quality. And I think that this is a task that it's, I would say, very difficult. And especially for data sets or sources that are unique. that is even more difficult to do. So if you don't have something else to compare your source with, then it is very difficult to try and find which is valid or which is not.
Right. Thanks. So there's one more question from the audience. And it's like Vad Alhoshan. It's like, for smart-based research, is there any linguistic restrictions or considerations over the user input to parse the related information?
To the best of my knowledge, no. There are some keywords and there are some labels that are offered as suggestions and to the user to try and guide them. But I think there are no restrictions to what can be written in the text box. I'm not sure if everything that it's written is interpreted in the query. And I think that that's why it is a live creation of the graph too. So as you type, you can see how this is interpreted and go back and change what you typed.
If there are no more questions, we'll probably wrap up this session. I'd like to thank the audience. Thanks a lot, Maria, for a very insightful talk. I'm sure everybody has a lot of things to take back on and explore as they look at RDF data. So thanks a lot.
Thank you very
and
much.
on behalf of the organizers, I would like to thank Dr. Seema Sundara, who is herself an expert in this area, for very smoothly steering this entire session. Thanks, Seema.
Yeah, thanks.
Thank you, Schema.
Yeah, thanks. Brian, we can probably stop the recording now.